So to explain spring force and Hooke's law, actually, for that example, I want to walk us through an example using what I will call a flat pinball machine, which we can literally just think of as a pinball laid directly horizontal. So you'll probably be somewhat familiar that pinball machines aren't actually laid horizontal. They have an incline to them. The reason for that is the ball will naturally roll towards the bottom of the incline. The pinball machine, the launcher for the pinball, has a spring mechanism. You pull down on the spring and it pushes the pinball up. And that's going to counteract gravity for a regular pinball, but because we haven't gotten to two-dimensional motion yet, we're going to pretend it's just flat on a surface, and I'm going to kind of represent that here as, let's say we have some compressed spring, and it is going to be compressed. Let's say this is its equilibrium position, meaning if I were to let go or uncompress the string, it would naturally bounce out and rest at that spot, right? And so this could be its change in position, or its stretched position we'll call delta x. That's its displacement, or in this case, it's a compression. It's displacement distance from where it's happy, its equilibrium spot. Hooke's law for the equation for a spring says that the force for a spring, or the force required to compress a spring, is directly proportional to the spring constant, which again we briefly talked about has to do with relating the substance of the spring itself, the type of material it's made out of, the thickness of the material, the length of the spring, a few different things involved in that, and then the amount it's being compressed. So and again, it's direct proportionality to this. And we're going to use the example of the pinball machine to configure essentially what the net force on a pinball machine would be if this spring were allowed to press on it. So that's kind of the idea behind this. So let's assume that our spring is compressed. Let's say there's like a lever holding it. So let's pretend that this is our like little lever right here. It's really poorly drawn, but you get the idea. And right here rests like a little iron, not sure what those are made out of, not copper. We'll say a little iron ball, and we'll say that this is decently heavy for the size of it. Maybe we'll say it's 5 kilograms. That's maybe a little too much, but you kind of get the idea for that. So that's the mass of our little tiny iron ball. So that's our mass. And we can actually calculate the net force if I were to release the lever that would propulse this ball forward. We could actually figure out the acceleration of this ball. For the next module, we'll expound on this and we'll get into motion. If it's starting at rest, how fast it's going to accelerate in its final speed. But we will, for now, we're just going to model its acceleration. Using Newton's second law, that the net forces acting on an object are equal to the mass times its acceleration. I can figure out how, once the latch is let go and the force can be applied to the ball, what's the acceleration of that ball going to be? Because essentially the force that's going to propulse the ball forward is going to solely come from the spring in this instance. And so I can, well, this is just going to be the sum of my forces. Currently at the moment, there's forces on my ball. Well, technically it's resting on the table or whatever, the bottom of the pinball machine. So gravity's pulling it down. The normal force is holding it up. We're just going to look at the horizontal motion, though. We're just going to do, so the free body diagram for this, I have gravity pulling it down. I have the normal force pulling it up, or holding it up. And once I release it, so currently right now there's no horizontal forces when the pin is holding the spring closed. But as soon as I let that go, there's going to be a propulsion force, we'll call Fs, for the force from the spring that's going to push it forward. So the net force solely in the x direction is just the spring force. So the spring force is going to equal the mass times the acceleration. And then I can substitute this equation for spring force in here. The spring constant, the displacement of the spring, that's going to equal the mass times the acceleration. And then I can solve for the acceleration by dividing mass from both sides. I get that the acceleration of the ball is going to end up being the spring constant, the amount it's being compressed, divided by the mass of the ball. And so far, I've only defined the mass of the ball. Let's say we knew, for example, that spring was compressed by, we'll say delta X would be compressed. Let's be a little somewhat realistic here, about maybe like 10 centimeters. So 0.1 meters in terms of compression. And then the spring constant, some of these are kind of high. We'll say 200. And that'll be newtons per meter, will be for the spring constant for this case. Then I can plug this in, and I can say, all right, well, this is going to be 200 newtons per meter times 0.1 meters, divided by the kilograms. This would be 5 kilograms. Meters cancel. A newton is a kilogram meter per second squared. The kilogram will cancel with this kilogram down here, leaving just the meters per second squared. I will end up with 4 meters per second squared as the acceleration that would happen on this ball. Another case that we will look at is if I have, so instead of looking at the flat pinball machine, we can look at what's called the hanging mass. So we will call it a hanging stationary mass example. And this is going to be particularly helpful when we do the lab for this module. We can look at it as, so a spring is attached to some fixed position, whether that's a ceiling. In the case of the lab we're going to be holding the spring, but we'll say that a spring is attached to some fixed position, and it has a natural hanging spot, and then let's say we hung from it a mass. In this case, we can call this one here, let's call this our mass. Now, if I took the mass off the spring, it would have a natural equilibrium position. So this is its change in position. This is basically the same concept except for it is vertical. And the reason the mass is going to end up being stationary is it is going to be exactly equivalent. If I draw the free body diagram, well, what's the thing pulling the mass down? Gravity. Fg, which on the case of Earth is always equal to the mass of the object times Earth's gravitational acceleration. And what's the thing holding it up? Well, that's the spring force, which is going to equal the spring constant of the spring times the displacement distance using Hooke's law. So what this is saying is if I hang a mass from a spring and it's stationary, it's not accelerating, it's not even moving. So that means that the net force in the y direction, which I only have net forces in the y direction for this case, is going to equal 0. So F net equals 0 because it's not accelerating. Then the spring force has to equal the gravitational force. And this is how we can actually determine the mass of things. This is actually, if you guys have ever used one of those hanging scales, if you go on like an airport, actually standing scales do this too, but hanging for the case of what we're looking at here, this is how scales work and how we can actually calculate how heavy something is. So in this case, then I would expand my equation, spring constant, the displacement, that's going to equal the mass times gravitational acceleration. I could figure out the distance it's going to stretch if I knew the spring constant and the mass that's hanging from. Let's say the mass, we choose a 10 kilogram mass. And let's say that we know we can calculate it's going to stretch. Goodness, we could have it calculate and stretch. Let's say this is a very big spring, a very big example. Let's say it stretches 0.5 meter. That's a lot, but again, this is kind of theoretical, we can postulate. And then gravity is a known quantity we discussed in the last video, 9.81 meters per second squared. I can then figure out, well, what is the spring constant for this particular spring? I'd solve for K by dividing the displacement to both sides. Mass times gravity times the displacement. I get that K is going to equal, this is going to be 10 kilograms. Gravity is 9.81 meters per second squared divided by the displacement of 0.5 meters. This is going to give me, remembering the spring constant in terms of its unit should be a Newton per meter. Newton is a kilogram meter per second squared. So this ends up being a Newton per meter. And then if I were to plug this in, I would get 196.2 newtons per meter as my unit.